So about 150 years ago, Charles Darwin famously misquoted, said it's not the strongest of the species that survives nor the most intelligent. It's the ones that are most adaptable to change. That's every bit as true today as it was 150 odd years ago when Charles Darwin said it. In fact, it might even be more true today. John Chambers from Cisco has predicted that at least 40% of all businesses will die within the next 10 years if they don't figure out how to change their entire company to accommodate new technologies. And that's what we're going to talk about today, is new technologies. My name is John Frizelle. I'm the Chief Architect with Red Hat Mobile, coming from Waterford, Ireland, where the Waterford Crystal comes from, down the southeast of Ireland. You can find me on Twitter at John Frizz and on GitHub at John Frizz. So what I want to talk today about is three disruptive, transformative technologies: mobile, microservices, and containers. I'm going to take a bit of a look at each of these, at how they're different from what came before them, and then see if we can find some common themes, common tracks between these three disruptive technologies. And then going to pull all that together with a live demo that looks at the Red Hat Mobile Application Platform and OpenShift as a way of bringing mobile microservices and containers together and being able to deploy and manage these technologies much more easily than you would without the software offered. So let's look at mobile. Kevin Systrom from Instagram said that people interact with their phones very differently than they do with PCs. And when you design from the ground up with mobile in mind, you create a very, very different product than going the other way. And that's incredibly true. I've seen many companies take existing web-based, desktop-based technologies and try and shoehorn them into mobile without really thinking about the mobile device or the end-user experience. And they end up typically with quite a substandard product because they don't stop and think about just how different mobile is. What are the requirements for mobile? How are mobile devices used differently to laptops and desktops in the workplace? So let's take a look at some of the differences between mobile and traditional web-based technologies. So with your traditional applications, typically you're looking at things that are system of record. You're typically interacting with direct back-end systems. And some of these web technologies are really poor. It feels almost like you're accessing the database records with the format of the data you're presented with. You typically find very large, monolithic applications with a lot of features rammed into them, and long development cycles, 6, 9, 12-month development and release cycles for these large applications, which makes them very, very costly to develop and results in quite infrequent and very large updates to them. By comparison with mobile, typically mobile is not going to be a system of record. The mobile phone in your hand is not going to be the back-end store for data. It's a system of engagement. It's how people interact with the data, pull data out, and push data in. Typically, mobile apps are much smaller. They're simple, nimble applications that are highly targeted to a specific need. They tend to have much faster development cycles. You're looking at weeks to months, in some cases even days for simple mobile applications. The short development cycle makes them much, much more affordable, and it really lends itself to a continuous delivery, continuous integration type model for deployment. When we think about how mobile applications communicate versus traditional desktop applications, well, with a desktop application, you're typically either on an Ethernet connection or on a good Wi-Fi connection. You have a strong performant network. Bandwidth is not a problem. It doesn't really matter how many HTTP requests your application makes or how big the payload is coming back. So you may be rendering a screen with 5 pieces of information, but you get a response back with 100 fields in it. For a desktop application, it typically doesn't matter. You have the computing power and the bandwidth to be able to deal with excessive information coming back in requests. Whereas with mobile applications, you're looking typically at lossy edge networks, best case scenario 4G, but realistically 3G or edge networks is what you're dealing with when you're looking at mobile applications, and in particular for field workers, people who are using a mobile application to bring them to the next job, to interact with the job. People will often find themselves in areas of low or no signal. In those scenarios, the number of HTTP requests you make and the amount of data coming back in them is absolutely crucial. You need to keep the number of requests as low as possible, and you need to keep your payload size as small as possible, returning only the information that the mobile application needs in order to do its job. If you have a mobile application where you've ported directly from a desktop API where it's returning 100 fields of data and you need 3, your application is quickly going to grind to a halt because it simply can't process the volume of data coming back when it's on lossy or edge networks. Something else to think about in terms of mobile is how are mobile applications deployed. So typically with web or desktop applications, an update or a release means pushing something out to the web server, and the next time users refresh their browser, they have the updated application. It's very simple. It can be done in a matter of hours, perhaps even minutes with good automation. With mobile apps, there's typically 2 distribution methods. You have enterprises distributing through private app stores, and you have apps in the public stores, the Play Store and the iOS App Store. Typically with the enterprise apps, using mobile device management software, you can force an update out to users' devices, but it'll often take days before all of the users are back online and have pulled down the latest update to the application. So straight away, you've gone from hours to days in terms of the update cycle for mobile apps within an enterprise. When you look at the public app store, it becomes even worse. First, you upload to the app store. Then you have perhaps 2 weeks of a wait while your app is reviewed before the app or an update to it goes live in the store. And then you have a period of weeks to months to never for users to update. You can't force people to update the applications on their device. A colleague of mine very proudly shows his device when he talks about this with about 150 pending updates for apps. People don't necessarily update their apps, so you cannot depend or rely on being able to push out an update to a mobile application, particularly in the public app store. So what does that tell us about how we build mobile apps? It tells us that we need to keep the piece that sits on the device as small and thin and lightweight as possible. The less code you put into the piece on the device, the less bugs you put into the piece on the device, the less often you have to update. So when building for mobile, typically what you want to do is keep the app as a thin presentation layer and shift all your business logic to a back-end server that you control. So that if you do need to update, if you have bug fixes in your business logic, you can push them out to an area that is hosted, that you manage, and you can get updates out as quickly as possible. Okay, so looking at microservices. So Martin Fowler, I suppose, would be pretty much recognized as the father or grandfather of the term microservices. And as he put it, the term microservice architecture has sprung up over the last couple of years to describe a particular way of designing software applications as a suite of independently deployable services. And those last 3 words are the key takeaway really for microservices: independently deployable services. So when looking at microservices, typically these are the kinds of things you're looking at or looking for, the kinds of things you're thinking about. They should be modular. There shouldn't be a lot of different functionality within a microservice. The microservices should be loosely coupled. Typically REST, HTTP requests, or message bus for communication between services. They need to be independently deployable. So if you need to make an update to a microservice, you should be able to push out that update in isolation from the other microservices that make up your solution. Typically, you're looking for a microservice to do only one thing and to do it well. So if you have a microservice that's responsible for processing orders, it shouldn't be concerned about users or suggestions or inventory. It should only be worried about orders. And it's worth mentioning, microservices are not really just a revamp of service-oriented architecture, which we saw over the last 10, 15, 20 years. Typically with SOA, you had an enterprise message bus that had the smarts of how to route stuff and where to route it, and then you connected applications onto it. Whereas with microservices, typically, they're deployed independently. The microservices themselves are the smart endpoints, and you just have DOM pipes, HTTP requests between the microservices as they communicate with each other. So it's not as formal or structured a deployment model as service-oriented architectures. So when we look at microservices and look at what came before them, which would typically be large monolithic applications, we see very similar traits to what we saw for mobile. Monolithic, multi-featured, long development cycles, costly to implement, infrequent, large updates, low release cycle. Whereas with microservices, we see simple, nimble, targeted applications with fast development cycles, making them affordable and very amenable to continuous delivery and continuous deployment. Okay, so containers. So Carol Mathis, an author of a recent Docker book, summed it up quite nicely. If deploying software is hard and time-consuming, and it requires resources from another team, developers will often build everything into an existing application in order to avoid suffering the new deployment penalty. So what does that mean, the new deployment penalty? Typically, when you're deploying a new application or a new service, you have to think about things like logging, backups, monitoring, what user will it run as, what security. There's a lot of considerations for deploying a new piece of software. But if you start looking at deploying these pieces of software as containers, it gives you a framework for answering all of those questions once and being able to deliver a new piece of software in a standard format that your operations or your system administration team can take and run and deploy very easily. So typically with containers, you're looking at things like very lightweight, fast to spin up, typically disposable. A new release or a new version of your application will be a new container. You throw the old one away. They're virtualized environments. They use things like process isolation and C groups and namespaces and resource metering to allow you to be able to constrain how much resources on the underlying hardware a container can take up. They're built as a set of layered images, which allows them to be downloaded much quicker. As it builds up the layers and builds a cache, it becomes much quicker to pull down containers. Typically, they're encapsulating a piece of functionality. Containers and microservices sometimes are almost used interchangeably. They're not. Containers are a very good way for delivering microservices. They tend to have a lot of the same characteristics and traits. And the other nice thing about the containers is you build them once and then you can run them on any environment that supports hosting containers. So you get the same results in your development environment, your test, your QA, and your production environment. So if we look at containers, and hopefully people are starting to see a little bit of a trend here at this stage, typically with a VM deployment approach, again, it's a lot larger than a container. You might have a VM with 32 or 64 gigs of RAM, lots of different applications running on it. The VMs tend to live for a lot longer. Updates to the VMs tend to be pushing out batches of software, which results in more infrequent, larger updates that are more costly. Whereas with containers, again, we're seeing the same things. Simple, nimble things, highly targeted to a need, fast development cycle, quite affordable, and very much lend themselves to continuous development and deployment. So, hopefully people can spot the common themes. Simple, targeted, fast, affordable, continuous delivery. And typically when you see those kinds of things, they will be talked about in terms of things like digital transformation, or agile delivery and development, or bimodal and fast IT. So when you hear those kinds of terms, typically it's talking about delivering things that are simple, nimble, targeted, fast, affordable, etc. Okay, so let's look at a demo to try and take this out of the abstract and pull it together a little bit. So, as I said, the demo is going to have two parts. We're going to be looking at the Red Hat mobile application platform, and we're going to be looking at that in terms of developing and deploying mobile applications and microservices and containers. We're going to be looking at OpenShift as the platform that is running and managing our containers. So with the Red Hat mobile application platform, what we're looking at here is a diagram of a recently released version 4 of the product. And with version 4, what it allows us to do is put this part here, the Mobile Backend-as-a-Service, It allows us to run that on OpenShift as a set of containers. And since OpenShift can be deployed on-premise, it allows this mobile backend piece to be deployed on-premise. And this is the piece that the applications, the mobile apps living on your device, will talk to this. So in terms of data security for business data flowing through an application, once you have that mobile backend on-premise, it makes it a lot easier to secure your data. The piece on the right-hand side is what we call the core of the mobile application platform. It's the developer studio. So this is where people go to set up and lay out their development projects, host their source code, host credentials, generate builds and deployments of their mobile applications and their microservices. It provides quite a large suite of functionality from templates and SDKs and tutorials and command line development tool that you can integrate into your own workflow, things like lifecycle management for being able to bring a project from development through test, through quality and into production, things like analytics and alerting, a private app store for enterprises to host their own applications, push notification support, collaboration, teams, things like that. We'll look at some of this during the demo. So then with OpenShift, the Red Hat Mobile Application Platform talks to OpenShift and deploys this MBaaS, this set of containers that support running mobile applications into OpenShift. So it talks to the OpenShift master and pushes a set of pods into the nodes that are hosted by OpenShift. And then that MBaaS is available to the applications to get deployed there for things like data synchronization and caching and analytics and events and alerting and things like that. So we have a little demo app today. So it's an app that allows scanning a barcode and looking up the data about the barcode. We're going to be using an external website called searchupc.com for doing the barcode lookup. It exposes a SOAP service that we can invoke, give it a barcode ID. It gives us back a CSV data set that we convert to JSON and then send back to the mobile application. It also has functionality for displaying a list of recent searches from the SearchUPC website. In that instance, there is no API available, so we're doing a little bit of screen scraping and pulling out some data, formatting it into a JSON response, and again, sending it back to the mobile application. And we also have a very simple mock service to simulate allowing people to order products after they've scanned barcodes. So in terms of how it's laid out, on the left-hand side, we have the mobile application. It talks then to a microservice that exists purely for servicing it. So this is back to what we talked about, mobile applications being different and keeping the client side as thin as possible, keeping the logic on the server side, and keeping the payloads that you return to the mobile application as small as possible. So that's what that mobile microservice does. It aggregates information from the 3 reusable services beside it, and those in turn communicate with various backend systems. In terms of what we're going to see deployed onto OpenShift today, we will have 4 containers deployed, hosting those 4 Node.js applications. And as I mentioned, the mobile microservice is there purely for the mobile application as an API server for it to get the data it needs. It ensures loose coupling between the mobile application and the back-end microservices that are in use. It trims down the payload to ensure only the data the mobile app needs comes back. It does some service aggregation, and it promotes this concept of a thin client, keeping the logic on the client as light as possible. Okay, so enough of slides. Let's take a look at the demo. Okay, so this is the Red Hat mobile platform. I'm not going to go into a great depth of detail on the various boxes we see on screen. There's plenty of other sessions on over the next couple of days to do overviews of the whole product. I really want to just focus on the mobile microservice and container piece. So the first thing I want to look at is how do we hook up the Red Hat mobile application platform to an OpenShift instance. So within the admin area here, we have this ability to define new MBaaSes. And here is one I made earlier. So we give it a little bit of information, the URL of where OpenShift is, username and password, a couple of other pieces of information, and then that allows us to connect the mobile platform up to OpenShift. Once we have the MBaaS target set up, we can then layer environments on top of that. And the environments give us lifecycle management. They allow us to deploy things into different stages of the lifecycle and promote both the mobile applications and that server-side code that will live on OpenShift through different stages. So facilitating bringing something from development through test and into production. Within OpenShift, so when we create the MBaaS target over here with the MBaaS ID John Friz MBaaS, over here we can see a project having been created in OpenShift that represents that MBaaS. And it has a suite of different things in it. This little diagram here shows all the moving pieces that exist within the MBaaS. So we have 5 different applications deployed within the MBaaS, and each of them has various pieces that make up how the application is deployed. So if we look at some of these, we can see, for example, this is our Mongo instance. This is a deployment config. We can see here in deployments the 5 applications that have been deployed. And if we want to drill in, we can look at the deployment config and see all the data on exactly how that instance is set up, resource limits on memory and CPU, replica sets, environment variables, things like that. So when you create the MBaaS within the Red Hat mobile platform, it results in these 5 services being created and Kubernetes pods being deployed within OpenShift to run them. One of them, a service called FHMBaaS, has a public API, and the Red Hat mobile platform will talk to it to deploy applications, pull data back out of the MBaaS and things like that. So that's the MBaaS part set up within OpenShift as a set of containers, without having to dig too deep into Docker or Kubernetes or OpenShift. There's a relatively simple way from within the mobile platform. Provide a couple of pieces of information, URL, username, and password, and you have an MBaaS set up and running on OpenShift quite quickly. So now that we have our MBaaS, we are able to set up a new project. And the one that we are looking at is the barcode scanner application. So similarly to the diagram that we saw on the sides, we have the client on the left-hand side. We actually have 2 clients. I'm working on an Angular version at the moment. It's not quite ready yet. We have that mobile-specific microservice in the middle, and we have these 3 reusable services on the right-hand side that are calling out to various back-end systems. So if we dive into these just for a little minute, preview is very small. We'll come back to that. We can see the details of this mobile application. It's a Cordova hybrid application. We can see our Git URL here for doing local development. And we can do things like build a binary of the application. So right from the platform, from your source code, you can come in here. You can choose your platform, what branch, what tag you want to build from, type of build you want, and then hit the build button. And if things were working, you would get a binary back. I seem to have broken something in the code earlier on, which is why I have 2 failed builds there. So I'm not going to kick off another build, but we can see from the successful one that we have the ability to re-download the application. We have a QR code, we have a direct download link, and a bit.ly link for installing the application on device, which I have installed here. Within the server side then, this mobile microservice, we can see that the application is running. We can see that it's running on OpenShift and which instance of OpenShift. Various other pieces of information, again, our URL for cloning the application if we want. And probably the most interesting piece here is the deploy area. So the deploy area is where you kick off pushing the code you as a developer have written into OpenShift. So by clicking this deploy button here, what's actually happening is the mobile platform is reaching out to OpenShift. It's passing over a reference to the Git URL where the source code is hosted, and invoking a technology in OpenShift called source to image, where within OpenShift, on the fly, a new Docker format image is being generated and will be deployed automatically. If we look in OpenShift, and we have a look at our mobile microservice, we can see here that there is a build running at the moment, and that build was triggered by us clicking the deploy button in the studio. So if we click into this, we can see the logs of the build that's happening. So this is in real time a new Docker format image being created within OpenShift, and once it's ready, it will be deployed, and then the latest version of whatever was in your Git repository will be live on OpenShift, in this case as an API server. You can see things like history of builds, how long they took to build. You can dig into low-level detail on the build configuration, which tells us what Git repository we're pulling from, what version of Node.js we're using, and all the information needed for actually generating the build. Okay, so we will just let that build run for a couple of minutes in the background. And let us take a quick look at this area here. So this is where we lay down and define these reusable microservices, the things that we had hooked into the project. So we have 3 microservices here that are being consumed by this project, but are designed and developed in a way that they're independent from that project, and if you had other applications or solutions that needed this same functionality, they can just pull in these microservices. Under the covers, they're very much like the mobile-specific one. They're Node.js applications that are deployed to OpenShift. They have a Git URL so that you can clone them down, do local development. And similarly, you have the option to deploy them, which will trigger the new build and push it into OpenShift. Okay, so that build is now complete, and we can see that the pod for build number 5 is on the way up at the moment. It hasn't quite started yet. So within another minute or so, there we go, within another second. So now that pod is up and running and ready to receive requests. The pod is fronted by what in OpenShift terms is called a service. So a service is a public route from the internet into a pod. So it's basically a load balancer if you have more than one pod, or effectively a proxy to allow requests into the pod. So if we click on that, we can actually see the code running live here. And for example, we can call an endpoint. We can cross our fingers, and we can see data coming back. Okay, so that's our basic layout for our project. We've seen it in OpenShift. We've seen a build go through OpenShift and a new container deployed. So let's now have a little bit of a play around with the application, watch some data flowing through it, and then take a little bit of a look at how you would do local development and how that whole development cycle fits into deploying things as Docker containers onto OpenShift. So just move that. Okay, so we have our mobile application here. Forgive the ugliness of it. This is why I'm rewriting it in Angular at the moment, but it's functional. So what the application is giving us is a list of recent searches, and they are the same recent searches that you will see if you go to searchupc.com. This list of 5 searches here is the same list we're getting here. Now, before I go any further, they're searches that random people on the internet have made. I have no idea what these barcodes represent. And when I was dry running this yesterday, 4 out of the 5 of them were women's underwear. I have no idea why, but just fair warning, I don't know what's going to come up when we click on these links. So let's try it. Okay, a runner, not too bad. Baby book, okay, pretty family friendly. And Barbie Dreamweaver, okay, much more family friendly. So in the background, what's actually happening here is the mobile application is making a call to that mobile microservice in OpenShift. It in turn is making a call to the reusable service to reach out to Search UPC and get the data back. So let's take a little look at what that looks like in terms of our logs. So this is our mobile microservice. If we go into the pod and into the logs, and let us bring up another search. So we can see in the logs here, we got a request in. Not quite sure why that's EDT. I think it's where the server is deployed. So our endpoint barcode read was called. That was the barcode. We see that we don't have any data cached. So we'll look at the logic at the code in a minute, but it's using Redis to cache results, so it's not hitting the backend, the Search UPC backend, too heavily. Since we had no cache data, we called out from the mobile microservice to the barcode service, and we got a response back, giving us the details of what the product was. Included in the details is an image URL. But we don't want to return the URL to the mobile application, because then it has to make one HTTP request for the data and a second HTTP request to load the image. So what we have our mobile microservice doing, once it gets back the data on the barcode, it calls out to an image service, gives it the URL, and asks for a base64 encoded image back. Puts that into the payload and sends it back to the mobile application. So everything the mobile application needs for rendering the response is in a single request, and all of the data that came back from Search UPC that we don't care about has been stripped out. So let's take a little look at that from a code perspective. So within our barcode mobile microservice, we have a barcode.js file here that handles the request for the recent searches from Search UPC and a request to read a barcode. So we can see here the logger statements that generated the output in the log file we just looked at. And the implementation then, quite simple. First, we check our cache to see if we have any information on that barcode. If not, we use the fh.service call. So that's part of the mobile application platform's server-side APIs for allowing mobile microservice to call one of these reusable services. So it's calling the barcode service, calling the right path, and passing in the barcode ID. If we get an error back, we return a message to the client saying that we were unable to reach the barcode service. Otherwise, we get the barcode information, check that there's an image URL in it, because some of them don't provide the image URL. And if there is, we call this image service, give it the image URL, tell it that we want it base64 encoded, and then when we get that information back, we put that into our barcode response. We then do some payload trimming. So there are a number of fields that come back from Search UPC that we simply don't care about. We don't need the image URL anymore because we've now injected the base64 image. Sales price, store name, these are not pieces of information we're going to render in the mobile application, so we stripped them out to keep the payload as small as possible. And then right at the end, we cache the response and we return it to the client. So we can see there in about 60 lines of code, we're calling out to 2 different services. We're trimming a payload size, we're aggregating data, and we're exposing a nice clean REST API to the mobile device. So the mobile device has no idea that Search UPC is involved or that we're pulling in a base64 encoded image. We could very easily switch Search UPC out for some other barcode reader system, and you wouldn't have to change anything on the mobile application because he's talking to the mobile microservice where you can make any updates you need to keep your API consistent so the mobile application has no idea what's happening in the background. In terms of the image service then, as an example, this one is incredibly simple. It's about 15 lines of code. It takes in the URL of the image, checks to see whether base64 is required. If it is, it requests the image, pipes it through an encoder, and then pipes the response back. So we're seeing data streaming through here. We're not buffering anything. Doesn't matter how big the image is. We're using pipes and streams to send the data through. So the memory footprint of the service is never going to grow large, regardless of the size of the image. If it is not base64 encoded, we simply pipe the response from calling the image straight back to the mobile microservice. Within the client application itself then, if we just refresh this, we can see that recent endpoint being called, the one that returns the array of barcodes. And we can see in the payload that it is simply, it's as small as possible. It is just the array of the barcode IDs. Similarly, if we click into one of them and call the read endpoint, again, we can see we're only getting the information back that we need for rendering the barcode search on screen. So the 4 pieces of information we need here: the image, the text, the price, and the currency. In terms of the order service, so when you have a product, you can say order this. It will make a call out to our order service, giving it details of the thing we want to order. In this case, our orders service is actually just a dummy service. Very, very simple implementation. It just stores the order information in an array. But again, this demonstrates pluggability of microservices. So if we were building out this and we actually want to integrate it with an order processing system, we simply switch out this dummy order service. We build out a new order service that integrates with our back end, and then we make whatever changes are needed in the mobile microservice, the guy in the middle, to be able to talk to that new order service and keep the API consistent for the mobile application. So we can completely change providers at the back end without the mobile application ever needing to know or care. Okay, so that's kind of our end-to-end flow from mobile application through mobile microservice into back-end services and out to external systems. We've seen log flows coming through the various components. And we have seen that our mobile microservice has some logic and some error handling in place. So if one of its back-end services is unavailable, then the whole thing is not going to fall over. So let's try simulating that. Let's take our barcode microservice. And let's spin the number of pods here down to 0. So effectively what we're doing now is stopping the barcode microservice from running. So when it starts receiving requests from the mobile microservice, it's not going to be able to respond. So let us see how our application deals with that. So we see we get an error response back, and we can see there's an error message there telling us it's unable to reach the barcode microservice. So everything continues to work from the mobile app perspective. It makes an API call, it gets a response back, but it's being told, sorry, one of my dependent services is unavailable. Let's bring that guy back up. Take a couple of minutes for the pod to start up. We will be able to see that in the logs. We won't be able to see that in the logs. Let's try that again. No, okay. Trust me, it is coming back up. So we'll just give that a minute. We'll come back to it. We'll assume it will come up. Okay, let's talk about local development now for a minute, because obviously, if you're building out solutions like this, you've quite a number of moving parts. How you develop it, how you deploy it is very important. So we saw back here in the Red Hat mobile platform that each of our applications has a Git URL. So we can quite simply clone the various repositories we need for running it locally. So here I have the client cloned. I'm using grunt to run it. Here we have the mobile microservice cloned and running, again using grunt. And I have one other service deployed. So I have the barcode reader service, the one that reaches out to search UPC, also running locally. Within my cloud app, there's a little bit of configuration needed here to tell the cloud app where its various microservices are. So we have a map here telling it, and unfortunately it's using auto-generated unique IDs. But basically what we're saying is, this first guy is the barcode service. He's running locally on port 8002. This is the image service. It's running in OpenShift. And this is the order service, which is also running in OpenShift. So once we start the mobile microservice piece running locally, it reads that deployment config and then figures out how it can communicate with the various other services. So within our browser, so I have this running just locally on port 9002. If we refresh this, it will call out to the recent endpoint. And in our console here, we can see 1214 calling out to the recent endpoint. So, for example, if we wanted to make a small change, let's see, what will we do? Okay, so this is our barcode searches. So if we wanted to, we could add a fictitious barcode, save that. It auto deploys, it's watching the files on disk, so it auto deploys. And then if we refresh this, we should see a sixth one coming back. Or not. Oh well. That's live coding for you. Yeah, imagine that had worked. Basically what you're seeing there though is a very, very quick development test cycle. You're developing locally, running locally. As soon as you make a change to the code, it refreshes your local configuration, and you can test your changes locally here. Mocking out or calling out to as many of the backend services as you want that you're not going to be touching. So you can call out to some in OpenShift. And in this case, we have one of the backend microservices running locally. We wire that up, through the configuration in the mobile microservice. And we have a local development environment where we have the client app, the mobile microservice, and one of the back-end microservices, all available for us to develop locally. I suppose the final thing to mention then in terms of local development is the feed-Henry command line tool, or the Red Hat mobile command line tool. So effectively what this is everything you saw in the Red Hat mobile product in the visual UI, available as a set of command line calls. So this makes it very easy for developers to integrate this into their own workflow. They can use the command line to pull down projects, to push projects, to trigger builds, trigger deployments, without having to switch from their development context back into a web application, which most developers don't like to do. You can also take this FHC command line tool. You can do things like integrate it into a CI/CD process. So call out to it, for example, from Jenkins. So you could have nightly builds where the latest version of your mobile application is built, the latest version of your server-side Node.js components are deployed, and run a set of smoke tests. So it's quite easy to integrate CI/CD into your development process using the FHC tool. Okay, so that's about it for the demo. One or two slides just to finish out with. If you want to learn a little bit more about containers, Eric Sauer is giving a talk on Thursday at 3:30 on migrating workloads to containers. And Josh Waldman is doing an interactive session on exposing legacy systems to your mobile applications. So I'm hoping that he will talk about a lot of the same kinds of things that we've talked about here, the reusable microservices for integrating with the back-end systems, the mobile microservice for encapsulating all of it, and then the nice thin mobile application to try and keep the update cycle for that as low as possible. Now the fun one, party! So Wednesday evening, 9 p.m. to 12 p.m., we have the mobile middleware and OpenShift party. If you call to either of those 3 demo pods in the partner pavilion over in Moscone West, come by and you can pick up a ticket for the party. So hope to see some of you there. That's it from me. So any questions? Not you. He's a plant. Security. Go ahead, Javier. Yeah, so what happened when I went to 0 pods? So let us have a look at this again. So within OpenShift, there's quite a lot going on. There is pods, there's builds, there's deployments, there's routes, there's services, there's image streams. There's a whole host of different things going on that can be quite nicely visualized through this here. So when we brought the number of pods down to 1, what we were doing was that blue guy there was scaling down from 1 to 0. So basically, it's the same basic idea as killing a process. Everything is still there, it's just not running at the moment. In fact, if we were to do it again, we should be able to see there we can see the blue guy in the middle has disappeared. So while we still have our deployment config and our build config here, there's nothing hooking it up to the front-end route that a user can come in through. So if a request came in, it would still get to the public route here, or the public service, sorry, the route, which would bring it as far as the service, which encapsulates the pods, but because we have no pods running, the request fails at that point. Any other questions? Yeah, so if not increase the number of services, there's always one service, that's the front door, but if we increase the number of pods, so let's do that. And now what we see here is 2 pods represented in the kind of architecture diagram, being fronted by this service that will load balance requests across both of them. In the background, you have Kubernetes monitoring the pod, so if the pod dies, if there's an exception thrown within the image and the pod dies, Kubernetes will automatically restart it. So you have quite a level of resilience in what's deployed even without horizontally scaling it, because you have the OpenShift platform constantly watching what's going on and restarting pods as and when they need to be restarted. So when we build and deploy from the mobile application, we're pushing across the deployment configuration. So this information here. So this is information coming directly from the Red Hat platform. That's not what I wanted to do. Telling it the various unique identifiers back on our side. It tells it how to deploy it, what type of strategies to use, what image stream to use. So this is when the Git repository comes across and this source to image process is kicked off that turns our Git repository into a Docker format container. This is telling it how to do that, and it's giving it information like environment variables that will be injected into the pod. So we're sending across quite a bit of information, telling OpenShift what to do, and then it figures out how to do it. It schedules the build wherever is available, and then once the build finishes, it deploys it. Yes, so we send over a request to an API, we pass it some configuration files, the reference to the Git repo and things like that, and then OpenShift takes that, figures out how to build an image, and run it for us. And then we have things like the history of the builds that have been completed previously here. Okay, any other questions? Okay, we'll leave it there, so thank you very much.